dimensions specified. Here 1 tells it to sum up rows. So the first row gets added to the second, and then that result gets added to the third, and so on. Let's see what this looks like. I'll comment out the rest of the code since it's of no use right now. You can see the effect of rows being summed, getting brighter and brighter as you go down. Here is the original image for reference. And here is the row-wise cumulative sum result again. Alright, so this takes care of summation in one dimension. As you might have guessed, we can take the cumulative sum along the other dimension of this intermediate result in order to get our integral image. Let's clean up and do that. So, as we said, the first cumulative sum is an intermediate result. Now we sum this up along the other dimension, that is, along the columns. The first column gets added to the second, and that result gets added to the third, and so on. And that's it. This is our integral image. Let's see what the result looks like. You can clearly see a gradual monotonic increase in brightness from top left to bottom right. That is to be expected, isn't it? Let's check if the two computed values were the same. And yes, they are indeed. Okay, so what about this crazy formula? Within the larger image, we have defined a window using x1, y1, x2, y2. The top left corner has coordinates x1, y1, and the bottom right has x2, y2. The first value, I, y2, x2, is the integral image value here in the bottom right corner, which is basically the sum of the original image from the top left till that point. We call this A. Remember B was this rectangle up here? Note that it needs to go to the column value x2 on the right, but needs to stop one short of y1. Otherwise, the values at row y1 will get subtracted from our final result. This is why you have a -1 here. Again, this was B. Similarly for C, it needs to go down to y2, but needs to stop one short of x1. Hence, x1 minus 1. Note that the region D that has been subtracted twice is only up to x1 minus 1, y1 minus 1. And that's exactly what we add back in. Clear? Now think of an edge case where x1, y1 equals 1, 1. That is, the top left corner of our desired region is at the top left corner of the image itself. These -1s can then result in invalid indices. To overcome this problem, MATLAB, for instance, pads zeros on the left and top. That is a single row of zeros. It increases the resulting width and height by 1, and it requires you to change the final computation expression. But this is just an implementation detail. Overall, I hope you can appreciate how vastly significant integral images are. Once you've computed an integral image, you can replace each of these summation operations, which involves probably hundreds or thousands of additions, with just 2 subtractions and 1 addition, right here.
So now that I can compute rectangles very quickly, I might want to look at a lot of rectangles. And in fact, for training their boosted classifier, these guys looked at over 180,000 possible rectangles that could be applied at sort of a 24 by 24 window. Okay? And here's basically what they're going to do. They're going to look for faces in 24 by 24 windows only. And they're going to take your new image and scale it to a couple different sizes and say, okay, can I find it in anywhere in that 24 by 24 window? Okay, so we said the first idea was to use these patterns. Well, remember we just talked about boosting where you look for weak learners, all right? Well, basically they're going to choose whichever features they can find that tend to be the best weak learners. So they're going to use, in fact, they use a thing called AdaBoost in order to do that. So you want to see which weak learners reduce the weighted training error the best? Don't you? Yeah. Don't you? Don't you? Okay, well, turned out these are the first 2 features selected, all right? That is, for a 24 by 24 window, if you have a face in here somewhere, those are the features that they're going to use. And you might wonder, why does it become those features? Well, take a look at it this way, right? It's basically looking for eyes, sort of darkish patterns in there compared to what's down here, okay? And then there is this patch here that says the middle of it tends to be brighter in the middle than around the edges. Just these two features, these were your first two weak learners. All right, so as I said before, so far our main ideas are we're going to use those rectangles as features, and it's really easy to compute them because of the integral image. And then we're going to use the discriminative ones as the weak learner, the weak classifiers. All right, well, we're using this within a boosted framework, so not to surprise you that we're going to combine them to make our final classifier. That's what boosting does. But the other idea they had was to form this thing called a cascade of classifiers. And it's such an important idea that I made it in italics, yellow, and red, okay? We're going to form a cascade of these classifiers, and we're going to reject clear negatives quickly. What's this all about? All right? So the second big idea of this paper, besides the integral image one, was the cascade. And here's the issue. Even if our filters are really fast to compute, so even if we can get these, compute these rectangles on a new thing very quickly, there's an awful lot of places to go search. How could we make the detection more efficient? And this was the insight. Almost everywhere in a picture is not a face. I don't care what the picture is, unless you happen to be looking at the 1972 New York Yankees like this, we got, 75 face. But even then, most of the locations are not a face. There's only 75 locations that are a face, and all the other locations, remember Kristen's little, those are not faces. So what you'd like to be able to do is quickly know that something is not a face, right? So you can move on. And if I say that something's not a face, I want to be sure that it's not a face, so I can move on. So what they built was a cascaded set of filters, okay? So at each level there's going to be a boosted filter, but here's what they did, all right? So you have a whole bunch of images, windows, scales, etc., whatever. You train a classifier. It's called stage 1, all right? And whatever it says is not a face, you're sure that it's not a face. So when you adjust your classifier, you adjust it so that it has no what are called false negatives. Everything it says is not a face is really not a face. Everything that you say is a face, you're going to put into another classifier. So you're going to train a second stage classifier. And what it's going to do is, remember, this is on training data, so it's labeled. You're going to give it a whole bunch of positive faces, but what negatives are you going to give it? The negatives you're going to give it are the false positives from the last stage. So stage 1, remember, we've set it so that everything it says is not a face isn't. But it says a whole bunch of things are a face. Some of those are wrong. Those are false positives. So we use those negatives plus real positives to train the next classifier. And we do that again. And what that gives you is a cascaded set of filters where when you apply this in testing data, you have to make it through all the filters, all the stages, in order to be labeled as a face. But to be rejected, you can be rejected quickly. It's just like dating in college, right? You can get rejected quickly, but it takes you a long time to get accepted. All right. Just as a quick summary, we have a whole bunch of images, faces and non-faces. We're going to train a cascade of classifiers. They used AdaBoost, all right, which is a particular boosting algorithm. And we're going to select out features and thresholds and weights, which you have to do in AdaBoost. And then what you're going to do is for some image, you're going to apply it to the window. That's where the face really is. We pick the window, we slide it around, and there it is, and it finds the right face. I have to tell you, this worked extremely well. These are some examples taken both from their original paper and some others. So they were showing it running on all of these different images, some of which are, shall we say, typical computer vision images where the face is right there. Some of them are much harder, right? Now you'll notice, and we'll get to this in a minute, this guy is missed. You know why he's missed? It's not because he's not good looking. I have no idea whether he's good looking. That's up to you guys. It's because he's turned this way. And the thing was trained on frontal faces. Here's some more examples. I love the Star Trek one that it worked really well, but for some reason Scotty there, James Doohan, I don't know if it's the mustache, whatever it is, This thing likes Vulcans more than it likes Scottish people. Can't explain why. But basically the idea is the thing was able to work extremely well. It also dates it a little bit because here's a picture of the Seinfeld cast. So that tells you something about when this work was done. Some interesting errors. Notice this one down here. Okay, so it got all the faces on the soccer player. Football for those of you not in the States, all right? But take a look at the ball at the bottom there, right? Now, if you kind of squint at that a little bit, oh, I'll just take off my glasses and look like that and say, oh, yeah, it's George. And they said, no, but it's a soccer ball. The distribution of the pattern was kind of close, and it labeled it. Here are some more examples. And again, you'll see that this profile was not done so well. So what do? Well, how about training some profiles? Again, train the classifier using the same types of rectangular features, and now all of a sudden you can find faces, these faces here and those faces there. A couple of cute things that were done by folks. They found faces in video. That was to be done easily, but the video came from broadcast video that had annotated subtitles, including characters, and they started to be able to associate different faces with different characters. So eventually, as you could see, it would recognize Buffy the Vampire Slayer, because after all, who would be complete without recognizing Buffy the Vampire Slayer? But the work was very cool. So here's an article pulled out 2007. So most of you have used Google Street View. Well, when Google Street View first came out, there were people's faces in it. Actually, it's not totally true because they knew this was going to be a problem. But as you can imagine, people didn't want their faces. And by the way, not just want. In the United States, you can push back a little bit in terms of faces. In Europe, you have a much greater right to your own face, or I should say to the image of your own face. So it was very important that Google be able to remove the faces of people from their street views. So to remove them, you have to detect them. And they're not going to pay 9 million undergraduates to sit there and click on all the faces, so that you run the recognizer. Here's a thing pulled out from iPhoto. Most of you have, I have an image in our introduction, on the back of your camera where it finds all the faces. Many of those systems use either the Viola-Jones method or some version of it. I do like, Lana had this picture of things that iPhoto thought was face. Here's a picture of a sort of a teddy bear made in chocolate chip cookies, and iPhoto thought it was a face because the pattern is about right. To briefly summarize the Viola-Jones face detector, a couple of key ideas. First of all, they're going to use these rectangular features, and really the big idea was the integral image that makes it easy to compute those rapidly. Second, they used AdaBoost for doing both feature selection and for training the classifier in general. We didn't talk a lot about that here. Sometimes I talk more about it, but these days you can just go look up AdaBoost. It's easy enough to implement. The really useful idea was the cascade filter. And other people have done cascades and various kinds of things, but the way it was applied to face detection was here. Training is training is slow. Remember those 180,000 different possible features, and you try them and you're looking for all these weak learners. So there's a lot of potential weak learners to choose from. But detection, runtime, is very fast. So when I pick up my little camera or I point my smartphone, it can find the faces very quickly. And it is really, really effective. It is rare to see a paper turn into both commercial technology and impact the field so dramatically, so quickly. And that's some measure of the effectiveness of the paper. And neither Paul nor Mike gave me any funds to endorse them. All right, so let's summarize boosting real quickly. It combines feature selection with classification. Remember that selecting of the weak learners? So you can think of that as sort of selecting, you can think of that as finding features. And pretty much any scheme you come up with for defining weak learners and trying them will work. The complexity is linear in the number of training examples. You basically trying different weak learners, you pick however many you want, and you apply them against your various training examples. We mention that here because the method that we're going to talk about, some of the methods we'll talk about later, become sort of somewhat quadratic because you have to compare each of the points to each of the other points. You don't have to do that here. Testing is very, very fast. It's very, very easy to run. You can write boosting code. In fact, many people have. You might ask, why wouldn't you write your own code?
Why wouldn't you write your own code?
Because some of the methods that we're going to talk about are actually the bookkeeping is very difficult and people use other libraries. And then when the stuff doesn't work, it's much harder to track down, was it the classification method, was it the parameters within, etc., because it's kind of a black box to you. Boost